Okay, hello, welcome back. Let's get started. We are in the Java EE course, and last time we stopped, I want to say on UDP, demoing UDP, and I think it worked, I think. Hopefully it did. Otherwise, what I'm going to do is kind of spend a few minutes, talk about TCP, talk about UDP, and finish up those examples, and then get into the RMI, which is what really we're supposed to be covering here. And so, in the UDP example, let me exit, go back a few slides here if I can get back. Here it is here. We loaded up a client UDP server, simple server, and let me bring it up in JGrasp actually. UDP server simple was the first example I believe that we went over. And I just want to kind of note a few things here and look at the source code. And then we'll compare it to the TCP example. And what do I have here? UDP simple client. Well, we'll start with the simple client first. Client simple. And what we have here is a simple old Java program that is going to perform a UDP connection for us. And this is the client part of it. And the trick to this, and the reason why I'm bringing this is kind of because I need to show you the differences between the UDP and the TCP. UDP is unreliable, works with the concept of the datagram. And so we have a datagram that gets passed back and forth. We make what's called a datagram socket, and that's a new instance of the object. So we're going to call the socket the new instance. So we bind the socket to a port, and we specify that because we have to have outbound communication from the client to the server. We don't have an inbound channel for the client, we just have outbound. So the server has inbound and outbound, but it's all using the same port, essentially. So the socket in this particular case is a new instance of a datagram socket. And we have the internet address, or the host, which is going to be the name of the IP address of the server that we're going to connect to. Because we're going to connect the socket from the client to the server through a port abstraction, and the host so we need the IP host address because it's really going over an IP network. And so the internet address, the host, is equal to the init address.getName, and the getName method, getByName method is going to get the name from the command line prompt, and it's going to parse argument number 0, which is going to be the name of the host. And then when we get the port on the server that is listening to the message, if you're following the little comments here. And then we're going to declare, we're going to declare a byte array to keep in all of the information that's coming through. In a TCP environment, we're working with a stream because we have a constant connection, and we get a stream of information, and we can take that stream and parse it into a string. We can do stuff with it. In a UDP, we're looking at getting it as a packet. And it's a datagram packet, and we're taking that packet and we're putting it into a byte array, and then we're going to parse it out, or we're going to make some sense out of the array to get the information out that we want. We don't really have a stream, so we're not working with like stream data. So we'll see the differences today with that. So the server here, we're going to get the port of the server and listen to it with the third argument, which is going to be parse integer parse init from the command line argument and make that the server port. So if the client starts up and says, connect to this server, and this is the port that the server is listening to. And then this is going to be declaring the storage area for the data that is sent and received. And so it's going to be a byte message that's going to be the message that we're going to send to the server in the third parameter, or third argument that we're sending on the command line. So when we type up the server, it sits there and waits. When we type up the client, we say, TCP client or UDP client space, the name of the local host or wherever we're connecting to in terms of the location, which is going to be local host because it's on my same computer. Port 7777, and then the message that we're sending. And the message is going to be put into a message byte stream because that gets converted to bytes when it gets sent as a datagram packet. So then we create the outgoing message packet to send from the third command line argument, which is the string that we're going to send. And so it's a datagram packet that we're going to use in terms of the object type. It's a datagram packet. So we have a datagram socket, and we have a datagram socket. We have a datagram packet. This is all UDP. And it contains the outgoing message. The outgoing message is going to be the argument and the server and the host and all of the information, because this is actually gets encapsulated in, next week we're going to talk about IP. This gets encapsulated into an IP formatted packet. So the datagram packet over, from terms of a UDP connection, the protocol for UDP is establishing the packet. The packet is being transported over the transport layer using IP, because we're on an IP network. If we were on an Ethernet network, we would have a different protocol for that, actually. But we're running this over IP. And then you might be wondering, well, how do we know we're on IP? Well, because this computer is connected to the internet, and I could send this to any computer on the internet, actually. I don't have to send it to myself, but I don't have any port open to accept incoming and outgoing traffic from my computer. Usually our ports are closed off. It's a security issue. But if I opened up a port, I could easily send it to one of you. So, and then this, basically here, we run a method to send on the socket, which is a datagram socket. We're sending the datagram message. And this is the outgoing message here. It's being sent as a parameter to the send method on the socket. And so we have the destination. This is we're going to print out to the screen the destination server and the message that we're sending. And then declaring the storage area to receive a reply back. It's the same thing. So sending and receiving is the same concept. So we have a datagram socket with a datagram packet that's being sent over it. And so here's just the reply message that we're going to send back to say, because the server is going to turn around and send it back. Say, hey, I got your reply, I got your message, and here it was. So we create a datagram packet object that accepts the data from the socket, takes the data from the socket, passes it, puts it into this object here, which is going to be the reply message, and then we can run, information to run a method receive on the socket. And when are we going to receive the reply message that's back, which is in the form of a datagram packet from the datagram socket. And then we're just going to print the information to the screen, do some exception handling. It's really nice to do that. And then print out, if we don't, in fact, this is a good for my memory right here. So print out the usage if we don't type it in correctly. So this is the UDP client simple, and then the server name, the port, and the message. And last time I believe we went over the UDP client server, and I think that's about as far as I got, really. Maybe we even loaded it up. But I'll load it up again just in case you weren't here last time. But the server is pretty much doing the same thing. So both parts of the program are communicating on this with the same protocols, using UDP with datagram packets and datagram sockets. So here we're just doing the same thing. We have a datagram socket, and the interesting note is that we only have one socket, one datagram socket. We're sending and receiving on the same socket. When we have a TCP, we'll have two, and they end up being threads, actually. And this is actually a thread abstraction as well, if you think about it, because we're connecting the ports via the thread, and we're waiting and listening on the thread. And the thread is nothing more than a running process or a running program, just like any other thread that you create on a computer. So. But we'll see that in contrast in a few minutes. So here's the datagram socket, the socket. We're going to try here. We're going to say that the port the server will accept incoming messages on is going to be 7777. This is good for me to remember, 7 sevens. And bind the socket to the port. So the socket that equals new datagram socket to this server port. Same thing as before, create the storage area for the received data and for the sending data. And we're going to do the received data first because the server's not going to respond until it actually receives something. It's going to sit up there, and this is the interesting part. So we put a while true in here. And the while true is really just a state machine, sometimes called an endless loop, that sits there and just listens. So it's going to wait for the incoming client, wait for the incoming request, and then when one is, it's going to create an incoming request datagram packet. So it needs to take in the received message, put it into a datagram packet, and then process the bytes out of that. It's just in a regular old byte format. Or we're going to put it into a byte array, I should say, and then process it as it comes in. And it's listening on the port, and we run a receive, the same command actually that we run on the client, we're running on the server to receive the information. And then here we have the outgoing reply that's created, and the outgoing reply is saying, get the data, get the length, get the address, and get the port from the incoming request. And the incoming request is that datagram packet. So we see that the UDP package for Java is basically giving us, or it's actually the .NET network package, is giving us the methods to automate it, to get the data, get the length, to get the port, get all the information from the datagram packet that was received from us, parse it all out, print it to the screen essentially, and then use that information to send a message back. So we send a datagram message back to the sender in this section of the code where we're sending, and it's the same thing as before, send, and this is the outgoing reply. And the outgoing reply is created here, and this is a datagram packet that's being created as the outgoing reply. And I just realized that this is kind of small for you guys. So it's an outgoing reply, and now that I'm done with it, we have the exception handling. So yeah, really a lot of good that was. Well, I sort of went over this last time, so we're in good shape. Someone remind me next time. So okay, so I've taken the liberty of opening up 2 windows already. So I haven't tested it, which I probably should have done, but I've changed the directory to the scode directory, and I've taken the liberty of compiling, but let me just do that right now. Just compile everything, so I've got at least everything is up to date. There we go. Unless I've made some stupid changes to it, which is possible. But anyway, so I'm gonna, in this window here, I'm gonna run the UDP and simple server simple. And what did it need? Well, here. Remembering the command line is a UDP server simple. It doesn't need anything. Let's see, just let me go back to the beginning of the example here. That one we need. That one I need to reference. There we go. It doesn't need anything. We just load it up in a box. And I'm taking this from the lecture notes. It's lecture number 4 that I still haven't finished yet, but I'm getting there. So it's waiting for an incoming request. So that's that one that had the while loop, the little endless loop that kind of sat there and waited for a request. And so if I open up my other window, this is where I'm going to load the client. And this could be, again, a client window on another machine. And then what I'm going to load here is I'm going to use, this is the name of Alpha, which is the name of a server. I'm going to use localhost because I'm on the same server. If I was on a different server, I'd use a different host name. And then the port, and then I'm going to say hello from the client or something like that. So UDP client simple is what I want. So in this window here, I'm going to type in Java UDP client simple localhost 7777. Make that a little bit bigger. Hello. Actually, I just said hello. There we go. And so I can see here, if I make this a little bit bigger, what I did was I sent it this funny hello. And localhost is 127.0.0.1, which is just the default set for localhost, which is probably the best way you're going to be able to test it. If you're doing it all on one computer, it's going to be the same on a Mac as it is on a Windows machine. The protocol is the same. So it says it sent the message, hello, and then it said that we received a reply back, and it received a reply back from port 777, and it was 20 bytes from this address is where it came from. So if I had sent it from a different address, the server would have known what address it came from and would have sent back the address of where I sent it from. And the reply message was hello, which is what I sent it. So on the server end, I can see that it received a message, hello, and then it just replies. I sent a reply back out. So we can sort of see that we've connected these 2 terminal prompts actually, which are 2 different ports. This guy is on a different. This guy sent out on a random port. I think it was like I probably sent it to 6666 or something. I'm not quite sure what I set it to. But the server was waiting on 7777. You can pick any port you want above 1024. Just anything above is open, not being used by the operating system, open for free communications. So. All right, so I'm going to kill this, and the only way to kill the server, because it's an endless loop, is to press Control-C. So if I do that, I'm going to kill the client. This is where we got. This is a review. This is where we got to last time. And the concept was very similar in terms of, see, now I can return to the lecture here, and I'm just going to do this manually so I can flip back and forth. But The concept is also demonstrated in the lecture there. It's the same, but you can see it live. And if you download the S code, source code from the bhacker.com, or actually I put it under one of the video links as well. You can practice probably under last week's link. You can probably, you know, it's a good start because one of the assignments for this course has you write a UDP and a TCP client, so client server program. So you can use that as a base, is what I'm saying. It doesn't do very much. It just sends a message back and forth. So TCP, and similar to UDP, but it fixes the flaws of the inherent UDP. As an example, I can run that, if I wanted to, I can run that about 5 times, and maybe one of the 5, the message isn't going to make it. It's not reliable. There's no handshaking, there's nothing going on. I just have a plain old client sending out. So there could be a case in which we have some lost messages. So it's not what I'd call reliable. TCP goes a step beyond UDP and provides that stateful and connection-oriented protocol, which means we have state information, and we know when the client is connected and we know when the client's not connected. We get feedback, and we have a lot more communication going back and forth. Here, if you remember, I was, kind of went through the code only because I wanted to show you that we manually receive something, we manually send something. We don't have a stream that's happening. We can't listen to a stream. We can't dissect stuff on a stream. We just open the port, send it out, and hope that it made it, and then catch it somewhere, and then send them, just manually send a reply back when we received it. So the send to the server may have failed. The send from the server back to the client may have failed. And it's actually kind of an interesting test. Run it 15, 20 times. You'll notice at least one time something's going to fail, either the send or the receive from the client or the server. So you've got a lot of potential for datagram loss, especially on a busy network. And a slow network, you're probably not going to notice anything at all. I mean, when I run it 10 times, I usually notice one time it fails. So in terms of the stateful, remembering that it has sent and what it ensures, and also fixing the order. The other test you can do is actually just set up a loop, send message number 1, 2, 3, 4, 5, and label the messages. And then you'll see it'll arrive 2, 1, 5, 4. It arrives in different orders. Because it's not managed. It's just throwing it out. It's like when you take 5 balls and throw it across the street. Whichever one was thrown the fastest is going to make it, essentially, first. So by contrast, TCP sets the order, sets the packet, and looks for the receiving and the sending, and manages the entire connection. So connection-oriented means that the packet is sent actually part of a larger conversation, and this is where I'm talking about stream. So we're going from datagram packets to the stream concept. And the stream concept looks at, it's different. It's a single thread that does not perform all of the communications. So we have a data stream to send and we have a data stream to receive instead of a port and a packet. So we have slightly different contrasts. Usually it's to handle is created for It's communications to create a new thread that is dedicated for incoming requests from a particular client. So each client has its own thread created on the server for its incoming request and its own stream. So we don't have to keep track of simultaneous clients. We just look for the right stream. We get the right information from the right client. In the datagram packet, if you notice, we ran the methods that said, get the port, get the client, get all that method from the datagram packet because we don't have that constant connection. We rely on the datagram packet information to dissect it, to figure out where it came from and what purpose, why was it sent to us, kind of thing. So the server can distinguish between multiple requests from multiple different clients on the same client machine because each client will be forced to use a different port as well. If you noticed in the previous example, I used port 777 as the server, and each client, you can actually load up tons of clients on the same port if you wanted to, and reuse the ports for everything, because it's not keeping track of there's no constant stream connection, there's no binding of any thread, so it's open, which means there's no management of it either. So you can't really keep track of clients through the port abstraction. So the programs that use TCP are similar nature. The details vary a bit. Because the TCP is stateful, we actually open up 2 streams, and I'll show you the code for that in a few minutes, an inbound and an outbound. They act as conveyor belts for the data to flow between the client and the server. And from a programming standpoint, we no longer have to use what's called the datagrams that I was showing you, but we simply read and write simple data types and string objects to the stream. it's regular old Java, in the Java language, it's regular old stream processing, which is nice. So it's a little bit easier in terms of not having to create a byte array, not having to take and parse each byte by byte, and turn it into a string to show it on the system output or whatever it is what we're doing with it. So the TCP server, the largest change, additional thread in order to maintain each one of the connections, and once inside the thread, the command are simply reading and writing the file, and it's very similar. So the example is the TCP server.java. And then we have TCP client.java. That's going to look like the same thing, but it's going to connect. So set the class path first. Well, yeah. Do set your class path first, otherwise you can't find the clients can't find it. Or change into the directory where you've got the files located. So I believe this was my server from last time. No, that was my client. Let me go back to my server, just for consistency's sakes. Now I'm going to load TCP server. Do I have to give it a port? I guess I'm going to find out. Yes, I do have to give it a port. So I'm going to say 8888. That's a good port, huh? Now listening on 8888. And then when I go back to the client, I'm going to run TCP client, same as before, same syntax. I'm going to run localhost, but this time on 8888, and I'm going to send it a message. So, this is easy. I just go back here and change this to, and I'm going to go over the source code in a few minutes. TCP server, client, I'm sorry, client. Connection refused. Exception received, because it's on 777. And this is interesting. We have interesting error message that actually kind of tells you something about the port information. In theory, you don't want to reuse the ports, because once you open it and bound it, you've got garbage sitting out there that might be attached to the ports. I could theoretically reload my UDP server on that port and probably establish another connection just fine with it. But the socket was not open, so there is no need to close it, and then the connection was refused because it wasn't an open socket. So the server actually opens the socket when the server loads and initializes itself in that wait condition, because it bound something to it. It bounded a datagram socket and received a datagram packet from the datagram socket. If I loaded up the server right now and I tried to connect to it, it wouldn't have a TCP socket. It would have a datagram packet, and it wouldn't connect either. I'd get the same message. So I'm going to change the port to the port where I actually have the TCP version of this program running, which is 8888. And now it works correctly. And it's the same feedback as before, but we'll take a look at the source code so you can sort of see the difference. The destination server was this one here. It was on port 8888. It received the message, and the message that it received was hello, that I had sent it. And the socket was open, so it's being closed. So it's being cleaned up. And if I go back to the server, I can see, lo and behold, on the server end, it was listening on port 8888. It received a connection from, and then it's giving me the port number, actually, which was chosen by random. It was 50430, which was the port number. Because on both of these examples, I actually didn't tell the client to use a particular port. I just said bind it to a port. Or maybe I did. I don't think I did, actually. I have to go back and look at it. But the server port was identified. So we have thread 0 to set up. And I'm going to show you that in a few minutes. So we set up a thread to receive the message, and then we set up a thread to send the message. So we have a sender and a receiver conveyor belt set up to toss back and forth between that server. And then receive the message, okay, looks like it did, and then it closed the socket on thread 0. So if we take a look at the source code, and control console, I'm not quite sure, shut down. Let's just shut that down for a second. Meanwhile, back at the ranch, my JGrasp died. Let me close this here. And I'm going to leave this up because I'm going to do the same thing for UMI in a few minutes. Open up JGrasp one more time. And it's kind of interesting though, but the connection is used, this technique, essentially, the TCP is used a lot actually. So if you've got like a virtual machine and you're bridging internet access between your local computer and the virtual machine that you're running with Parallels or with VirtualBox, it actually uses the port and it uses the IP address, and it actually performs a TCP connection through the software abstraction to bind, or to basically connect the two items. So let's see, what I'm looking at right now, what I'm interested in showing you is the TCP start. So we have TCP server. Let's take a look at that one first. TCP server, and I'll make this big so you can actually see it this time. There we go. UDP server. Okay, that's the wrong one. Alright. And we want TCP server. TCP server. There we go. Well, hopefully you remember the datagram packet from the TCP server, from the UDP server. And we kind of saw how that was put together. This one is a little bit different. So this one here is going to go TCP server. This is just going to start up. And it's going to tell me if I didn't, the usage information, if I didn't put it in correctly, assuming that we didn't get the number of arguments that we were expecting. Then what we're going to do is a try here. We still have a socket. But what we're creating now is we're creating a server socket. Server socket, the socket. The socket is going to be a server socket port. So it's looking at, in the server port, we're parsing the integers that we're sending on the command line. So I said 888, so it's going to take that, put it in there, and create what's called the server socket in terms of the abstraction. So as a server, we're going to listen forever. We're going to set up this little loop here, while true, which is the same code actually for the UDP server. But you notice we're not using any datagrams in here. So we have a connection counter. We're going to keep track of the number of connections, because then we can keep track of the number of threads that we have open. So we're going to listen for the next incoming. So we're still using a socket abstraction, and the sockets are bound to ports. So we're listening to, on the client socket, we have a server socket and we have a client socket. So we have a socket that is sending, and we have one that's going to be receiving, essentially. So listening for the next incoming request on the socket, client socket, which is going to be equal to the socket.accept. So we're still using, this is the same we saw before. We're still accepting and we're still sending and receiving on the socket, because this is all socket abstraction. Display the vital statistics of the caller. The caller, we get remote socket address, get the port, get the information from what we received in. So they received a connection from. And then for the new connection, it's a spin-off of the thread to handle the communication for the specific stream that we receive. So that, note that each connection will require its own client socket. So the server's got a server socket that it opens up to receive requests. And then for each client that connects to it, it creates a new thread. So each one of the clients has got its own socket. And so we can keep track of the number of clients, so we can keep track of who we're receiving information from the stream that's coming in from each one of the open threads that we have, which is different. So you can kind of see that this has got a little bit higher overhead than the datagram. So this is why, going back to what I concluded with last week when I talked about instant messaging programs, it's a datagram application. Could you imagine how many people use Yahoo Messenger? Just think about it, or Google Talk, or any one of those text messaging programs out there. Do you really want to create a thread on the server for everybody? No, that's way too much overhead. This server runs slower. With more simultaneously connected clients on this TCP server is going to shut it down. It's not going to run. It's not going to be able to support all the threads. It's going back to what I was saying about CGI and the entire concept of clients connecting to the server and running a program for TCI to get some internet functionality. Slow, because the server has to create a new process for each one of those clients that connects. So if I were creating a instant messaging program, actually text messaging works in a similar fashion. If I were creating a instant messaging program, and you can do this, actually I used to have this as an assignment for the class, but I took it out because it was a little too time consuming, but it's actually kind of easy to create your own instant messaging program, your own Yahoo messaging, because you just set up a server that accepts connection datagram packets from the clients. The clients have addresses. So the packet contains the sender, the receiver, and the message. Right? So the packet gets sent. The server parses the sender and the oh, this came from B Hacker. It's going to A Jackson. So, and we know A Jackson's on port 5. Okay, whether A Jackson is connected or not, we don't care. We just, it's a traffic cop. It just routes the messages back. And we saw the server accept a message from a client, take the client message, turn around, send it back to the same client, because that's all it really knew about. Because all we sent it was that little diagram packet. So we just add one more thing. We add the receiver, and then the server acts like a traffic cop routing the packets. Who knows if the packet's ever received? How many times have you sent a text message, instant message, and it gets there out of order? Yeah, it does get there out of order because they're just flying through, and there's no need. If the person didn't get the message, just send it again. You know, and actually it's pretty reliable if you think about it. Every time that I've used instant messaging, it usually makes it. Occasionally something gets messed up. But for the most part, for the kind of application that it is, it doesn't have to be 100% reliable, you know. But that's like most of the, and then what does it require? It requires a socket. It requires a port. So instant messaging programs in the earlier days opened up ports on computers because it needed a port, you know, 8888777, and you needed to open it up. And so if you open up a port on the computer, you're letting traffic in from the internet. And it's unrestricted traffic. It's just coming through the port. Because any client, any server can send something to your port. All you need to know is the IP address and the port. So in the original security issue with instant messaging was sniffers that would go out, look for open ports, find an open port, send a virus, send a worm, send whatever you want through the port because it's sitting there open. Well, it was a major security vulnerability. So programs have advanced to more sophisticated protection mechanisms and things, and you know, and better techniques. But it just started out this way. The history of instant messaging. It's datagram packets. So long story short, it was not a huge invention. It was very easy to put together. You could create your own. The only problem with that is if you're not doing it within a private network, make sure you got something watching that port and only block traffic from everything but the instant messaging program that's accepting it, which means you have to install a firewall and you got to install software that protects and add features to your program that's going to protect from unwanted traffic coming in. All right, going back to streams, a little bit different. Instead of going through an open port, we set up a stream. So, and this is the server parties accepting a stream. He's receiving a connection from a client, and we have the client socket. We're going to get the port from the client socket in which the client has connected to the server. So for each new client, it spins off a thread to handle the communication for that specific stream. Note that each connection will require its own client socket. So we have client socket new client equals new client socket on a client socket. And then we're going to essentially increment a counter to keep track of how many client sockets we have open. Do some exception handling, no problem. And then we have the client connection. So this is the interesting part. So this is the class here for the TCP server. Inside of this file we have the subclass that's being used in here, which is really a separate class in itself called the client connection. This is where we have the thread concept come into place. So we're creating threads that are going to be bound to each one of the client connections to the sockets. We have the threads so that we can keep a separate line of communication between each one of the clients. So the client connection, which is what we're creating, our threads in terms of the extraction. It extends, should be on the other line actually. It just goes up here. There we go. Extends thread. So it doesn't really matter. It can be word wrapped, but the data, and this is the interesting part. So before we had datagrams, datagram packet, datagram socket. Now we have data input stream, and we're going to call the input stream in, data output stream out. We still have the socket, and the socket is going to be the client socket. That we're going to call it the client socket, and that's what we've been using up here in the main server program. So this is the objects that we've been creating instances of from the server. Probably should have started with that first and gone back, but this is sort of backwards. But long story short, that's what this means up here. There's no such thing as a client socket. It's created down here. Here's the socket is the client socket. the client socket is the socket. The socket is the thread from the datagram stream that's being used to send and receive. So this is the constructor. It will set up a new client connection so that the thread can communicate. What's it doing? It's creating a new socket, the in socket, integer in identifier to keep track of each one of the sockets. So what does it do? Is it tries client socket is equal to create the variables here, try and connect and bind the port. So it displays the vital statistics, hooks up the plumbing. Here's the hook up the plumbing part. So the in, which is a data stream, is where'd it go? I highlighted it. Oops. There it is. Yeah, I did highlight it. New datagram input stream, and it's a client socket.get input stream. So the input stream as a concept is coming from the socket. It's coming from the client socket. Client socket is a thread that's being used to bind the client with the server through the ports. So it's still using the socket. The socket's attached to the port. All socket abstraction for both UDP and also TCP, both socket abstractions. So marks the thread is startable. Thread this dot start does some exception handling. In the run method here, we're going to read in the message. So this, and we can, because it's a stream, we can use the string object to hold the data. So string the data is new read UTF that we get it into an ASCII format essentially, text format, unified text format to come into the data. So we're reading it in the form of text, which is just this is just an automated method that you can run on the stream to convert it to a text format to make it into a string. So you can load it into a string class, and then print something out to the screen and say, this thread received the message. It's what we saw actually. And then the output stream, send a message out with the receiver with the message that it has been received. So we get the out.write, write this to a text format, receive the data, and print it to the screen, and do some exception handling. And then we have closing the sockets here. We should have closed the UDP sockets as well. And then we put a message here closing the socket. That was that little text message that came out to the screen that says closing this socket, closing that socket. So go ahead and play around with the examples, the UDP and the TCP, and you'll sort of see how that works. And it's interesting to take time to actually kind of look at the socket stuff, because then when we go into UDP, you'll see, well, the abstraction is a little higher up, but it's built on TCP. And so we'll see how that works right now, actually, unless we have questions on UDP and TCP. Some of you guys have probably already had that. It's typical. You get that in an undergraduate networking course. It's kind of typical stuff, but, which is you spend more than a couple lectures on it too as well. So definitely at a slower pace. So today we were supposed to talk about RMI. We're on schedule. So now we know the pros and cons of UDP and TCP, and we know that it's the underlying protocol that's running on top of IP, and we know that the concept essentially, where did I start here? RMI, here we go. The concept essentially uses a socket abstraction that binds ports using either datagrams or streams of information. Very similar. Both of those two technologies are very similar. So take it up a little bit. Provide distributed objects. How can you put objects through that? Hard. Because we've got streams of data, or we have data packets that are flying back and forth over a network. So problem scenario came around and said, well, what's a method invocation? Well, what about method invocation? So when we write a Java program on our single computer that we're running here, and I write hello world, and hello world opens up a date and a month object, and it makes a hello date and a hello month. It keeps track of my calendar or something, and it creates instances of these objects. So this would be called local, because it's on my local computer, and remote is something that's not on my computer. So if I were to take and create a main program, a driver program, and create an instance of date and an instance of month, or whatever it was, calendar, whatever I said, the invocation of those methods and those objects is a local perspective. It's usually loaded in the same directory unless I set a class path and I put the objects in another directory on my same computer. If you had, over in your computer over there, you had the month object and you had the date object, and I had a main driver program over here, and I wanted to invoke those objects, that would be a remote invocation. And if I wanted to run a method on those objects, that would be a remote method invocation. So most likely, however, I'm not going to make instances of those objects on your computer. You're going to make the instances, and the objects are going to reside on your computer. I'm just going to want to invoke methods on those objects. Why do I want to do that? Because I'm distributing my application on many different servers, and it's usually a client connecting to a server that wants to use an instance of an object that exists on the server instead of on their local computer. Why do we want that? Security, for the same reason why we have server-side scripting, server-side programs. It replaces a lot of other technology, makes it truly object-oriented, and it's really what's called the object-oriented client-server environment. Because we still have a server, we still have a client, but instead of sending text messages back and forth, streams back and forth. Yep. Yeah. I'm not operating the program, I'm operating the method invocation. So if you understand object orientation, you know everything is an object. And even main is an object. What does main do? Well, it makes instances of other objects. Those are invocations. An invocation, to invoke an instance of an object, means to create the object. To invoke or to run methods on objects is a method invocation. So RMI, which, looking at this slide here, remote method invocation. So we're not actually starting and creating instances of objects. Those objects actually already exist. And what we're doing is calling to the server and saying, I want to run this method on your object. And then the server says, okay, here you go. And the server serves it up. So in this particular environment, we could have one object created that was controlled by the server, that was managed by the server. So the server creates all the objects, and the server owns all the objects. The client is just running methods on those objects through RMI. And so now we can have one object of each type created. Efficient. So rather than every client who connects to the server getting their own instance of the object, which is what you get when you run everything on your own computer, every time you run Hello World with all those dates, you're creating new instances of the object. It actually takes up resources on your computer. If you took all those, put them on a server, created all the objects, had them ready to go, clients could connect to the server, all of them connect to the same instance of the same object, only one. You can have thousands of objects and serve millions and millions of clients. It's efficient because each client that connects to the server isn't creating their own instance of the object. They're not reinventing the wheel. They're just using what's there. So what we have is an object manager on the server side. And we have interfaces. So it complicates things because, well, can you imagine the security problem? Any instance of any method could go over and invoke any method on any object over there on the server. That might actually propose, more than opening up ports on a computer. That can actually really create some security issues. So we have what's called a security policy that we set up, and then we have a kind of an object broker, which is how Corba works actually. Corba is a true object broker. It came around before RMI actually, and I'll talk about that next, but no, probably next week or following weeks, but it's coming up soon. Long story short, RMI provides communication between distributed objects. So now they're distributed, they're on other computers by means of a remote method invocation. So RMI stands for objects that can receive remote method invocations that are called remote objects, and they're implemented via a remote interface. So the remote interface is, this is interesting, it's kind of like, believe it or not, this is really weird. If you take, for some of you who know C++, or Objective-C, which is kind of similar to C++. You know, you got that .h file, you got the .c++ file, when you program it correctly in the object-oriented world. They used to call the .h file well, in Objective-C they call the .h, and we have a .m. The .h is the interface. It's the contract that tells you what the implementation actually is about. And in .h they call that the specification. Sometimes people call it the interface as well. And it's a header file that contains function prototypes that lets you know what's in that object file, because when you compile the .c++ and you compile the .m, you end up with a .o in the C++ world, or the C world. And that's the object. And you don't want to keep opening up that object and using it. You have the interface to it, which is the sort of the contract, or sort of the blueprint of that. It tells you all the public information that's available. So in Java, how are you going to know what methods exist on those remote objects? And which ones are you going to be making available remotely? So we don't know. So we create an interface that sets the contract, that sets, this is a whole list of prototypes of all of these object methods that you can run. And so these are the ones that are going to be available. So there's a few more pieces to the puzzle that we can figure, so we can establish the interface, establish the remote object, take the remote object and make it work from a remote location. So we could do an invocation. And I'm going to see the whole thing work in a few minutes. So we have an extension of the local method invocation that allows the object living on one process to be invoked through an object living on another process. So we have inter-process communication that's going on. How does this fit into the system? Well, we have the RMI engine that we run, which is the middleware, the events. It's also RPC, remote procedure calls, events, all sorts of different things that run on top of other protocols that run on top of the operating system. So it's another layer of stuff that we're loading on. If you've installed the Java EE version, you've got RMI classes and you've got everything you need for it. So interfaces in distributed systems. So the interface, as I was mentioning before, it's really not a .h file. It's a separate file in the Java world. And just to fill the pieces in on that, we also have a policy file that sets restrictions as well that you'll have to create. And you can actually just set a generic policy file that just opens up everything. But in the real world, you want to set security. That's an issue. Not an issue, but it's a concern for most people. So an interface specifies the procedures that the variables can be accessed from other modules, in which the interface tells us what the public interface is from a programmer's perspective, and from a user's perspective, what methods are available. What can we invoke? So modules are implemented so that they hide all the information about the implementation except for what's available through the interface. As long as the interface does not change, the implementations may be changed without affecting the module and the behavior. In a distributed environment, the modules can run in separate processes as well. You cannot access variables in a module in other processes. Now, there's no direct variable access, which actually kind of follows through the entire philosophy of, if you took my object-oriented programming in Java course, and I said always make the variables private and make the member functions public, because you can't, even when you get into the Java world of RMI, you're not going to access any variables. That's unheard of. Nothing is going to be available anyway. You're running through a public interface, and the public interface is going to be those methods that you've created, the sets, the gets, all of that stuff. To run something on that method that's sitting out there, on that object that's sitting out there, whether remotely or locally. So here's the other interfaces as well, and we need the interface in the distributed world because we just can't go over to that computer and see what's on it. It's kind of like the poster or the road sign that tells us what's there. So parameter passing mechanisms that are called by value, and they're also called by reference, used in local procedure calls, do not work in the distributed system. How are you going to send parameters? How are you going to change memory on the server? You're not going to. You're only going to be allowed to send what you can. Uses input and output parameters that are used for passing between processes instead. So there's no calling a method using parameters, which is interesting. We'll see the differences in a few minutes. So pointers to one process are not valid in other processes in the remote computer. No pointer passing allowed either. Well, we don't have pointers in Java anyway, but the concept doesn't work anyway. So here's how it works. We have object over here, the remote invocation is occurring from A to B and B over here, it might be local. This is all local for B. B calls to C. B might use a local invocation of this object here, might go to E. E might actually do a remote invocation over here. So we take all these objects, we split them out over multiple different servers and computers, and then we remotely invocate instances, or we run methods that are on objects that are already created by instances that are residing everywhere we want to. Why do we do that? Well, we can split the functionality out. And if we go back to week 1, I talked about tiering. We can have a persistent tier, we can have an application tier, we split it all out, and then we can have functionality that makes sense in terms of the organization, and it's not all on one computer. It's like fault tolerance and all that other stuff I talked about earlier in the course. So here we go. The Java RMI provides an adapter that effectively hides the network from us. So instead of allowing us to simply look up functionality that we want regardless of where it actually exists, we use it as if it was locally. So it's used as if it was locally available. The level of complexity obviously increases a little bit once we decide that the distributed objects is going to be in the Java system. So what we're doing is we're assuming that we started with 2 programs, with one calling the other. Now we introduce the following elements. So this is what I was talking about before. We have the interface. The interface that explicitly states what functionality is remotely available. Just like a specification file or an interface in Objective-C. The server, well, we have to have a server. We're going to have a client too. But the server that provides access to the remote object, and then the RMI registry that links up requests from the client to the remote object. So the RMI registry is the engine that's running as the middleware. We have the stuff over here. We have the stuff over here. we have the connection because we're running over IP, hopefully, and same ways we run to UDP and TCP over with ports and IP and stuff like that. But the RMI registry is the brains of the operation. It's keeping track, it's registering who's contacting who and who's allowed to contact who and what's available and what's not available, and it uses the interface to get the information from. So here's kind of like what it looks like. Here's the overview of the interface. Here's the interface out here. Here are the classes in here. Here's what's available. Here's what's been implemented. Here's the IO exception that works with it. Here's the remote server with the remote objects on it. So we do the same thing as before. We load up the registry. We load up the server object. And the server object invokes the remote objects that are going to run on the server object. And then we load up a client and we connect to it. And hopefully it works. As long as we've got security set correctly. So here's our example. So we're going to start with 2 Java classes that are RMI enabled and then adapt them to operate in the RMI world so we can see exactly what's needed. So I'm going to take a non-RMI application, just a regular old Java application, and then make it work through an RMI interface. And this is all in the S-code file that you can download as well. So let's imagine that you've devised an auto-registration process class that, you know what class you're registering for is going to tell you whether the class is full or empty. So you can, we're just going to hard set a class in there, and it doesn't really do anything. It's just going to come back and say full, empty. So we have the ask the registrar.java. So this one is the ask the registrar class, and it says if it's uppercase, change it to lowercase, and here's the class here. We send it, it tells us if we put in CS483, it's going to say if that's the class, we're going to say it's registered. If not, no positions are available to be registered. It's just doing a simple if-else check on a variable. So if the class includes the words 483, CS43, and it's case sensitive, then the class must have some spots open, otherwise the class is full. Only one class is open, I guess. And here's the Java application to invoke the functionality. It's called localstudent.java. Localstudent.java is a regular, by the way, this is just a regular old class that we created, regular old Java that we did in the object-oriented programming in Java class. It's just an object, kind of like date or month, but it's ask the registrar. And here's the local student, which would be the client program on the local computer that would make an instance of this object. Here we have ask the registrar equals current registration status, which is equal to ask the registrar with the student class. So it makes an instance. This is the program that makes an instance of that object. So in other words, in order to work, both classes need to be in the same directory, or the class path must be set. Yeah. Here's the results when we run it. I'm not going to run it because it's kind of stupid. We've seen Java programs run, right? It's all in the same directory. It's all on the same computer. It's one program running in the other. So we start up, we say Java local student space, the name of the class, local student running, registration is, you are registered, local student finished. So this local student class made an instance of ask the register, and it sent it the method, ask the register about 4380, actually probably used a constructor for it. And the ask the register came back and said, yeah, you're there, okay. So it's one class making an instance of an object of another class, sending it a string and asking it if it's available. So let's take it and convert it to a RMI program. So we have one object that's making an instance of another object, but now we're going to put one object, local student, is still going to be the client, but the ask the register is going to be on a different computer, and we're going to connect to ask the register through a remote invocation instead of a local invocation. Hopefully you have followed me so far. If not, you're going to be lost when the example starts. Now we seek to move the ask the register service to a remote server so that we can access it through multiple locations within the university. Otherwise, it's all on one computer. Let's put it on a server so any student can ask the register from any computer, from any location. So the first step is to decide what functionality should be made available. Currently, ask the register class has two member functions and a constructor, and it gets the registration status. Doesn't really have very much. The constructor will not be available remotely, and so we need to create an alternative method to set the location. So when we make an instance, and here's the actually ask the registrar. So this is the constructor that we're setting, and we don't actually have one. We don't have a non-constructor that takes the class in and sets the local variable, the class, to the class that we've passed to the constructor. So we would have to rewrite this class to get rid of the constructor. So when we're making remote objects, no constructor behavior. Because can you imagine what would happen? The object is already made. If we relied upon the constructor behavior, we'd have to make a new object every time an object was invoked. So instead we create the constructor behavior into a regular old method without using a constructor. Because these remote objects are already, there's instances of these objects already created. And if you remember back from object orientation, the constructor is invoked when the new instance of the object is created. It's the only time that it's used. So we're not going to rely upon the constructor. We have two functions we're going to do. We're going to do a set class and a get registration status. And they will be available through the remote invocation, so we can create an interface deciding the details of what we're going to do in terms of this decision. So we're going to have both of these two methods available, plus we're going to create a method to set the class information instead of using the constructor. So you need to enhance the object so that it can be used remotely. And here's pretty much how it works, actually. Here's the big picture. So we have the client, we have the server. This is the same as UDP and TCP. Instead, now we have this RMI registry that we load up. RMI registry takes and performs the communication between the client and the server. It's the middleman. Make it a little bit bigger. The middleman. And so the client determines the remote location from the registry. So the registry can keep track of this server, that server, that server, tons of servers. It's all run through the RMI engine, keeps track of the location of all of the remote objects that are available. So it's got the interface, the contract that's going to be loaded. It returns the object location. So first the client goes to the registry and says, where is this object located? I need to run this method from the ask the register. It comes back and says, hey, it's over here. Okay, so then the client invokes the remote object over here, because this guy gave him the location. It's like the traffic cop again, sort of. And then the functionality is executed and then it goes back to the client, which is actually kind of simple. Think about it. But we have to remember we have to load the registry. If we don't load the registry, we don't get this. We don't get client server. So it's client server / registry. But it's not just this client, it's all clients. Excuse me, it's not this server, it's all servers. So it's kind of interesting how we can create a distributed versus a sole client server. So this actually leads to the the first concept of distributed computing from a Java perspective. So here's what the Ask the Register interface looks like. And we're not going to write it. Instead, I'm just going to show you the example of it. And then in one of your assignments, you'll be able to write it yourself. And you can use this as this example actually works. So you can use it. You can use it as a template to start yours because it's all going to look the same after a while. So we load on java.rmi. And then we have the interface, Ask the Register interface, that extends remotes. And then we have a set class, and we have a get register. What does this look like to you? Kind of looks like a .h file, sort of. What has it got? Function prototypes in there. It's the interface, just like we would be creating an interface, but it's not a .h or a well, actually it is .h in both Objective-C and in C++, but it's .java because everything in Java is Java. We don't have interface files in Java, separate like header files. But this is equivalent to a header file, actually. This is a template. This is function prototypes of the functions that are going to be available, the methods that are going to be available, and the object that we're going to create in a few minutes. So remember, an interface is the contract that the class can choose to implement. So there's no actual code in the interface itself. It is just prototypes of all of the methods. If you are familiar with the header file, the .h file, just think of it as an elaborate .h file. Not elaborate, actually, it's the same thing. So we have a new version of Ask the Register. We're going to see Ask the Register remote. I've already created this for you, in which we're going to import the Java RMI, import the Java RMI server packages at the beginning. And then we're going to inherit from Unicast remote object parent class, because it no longer comes from object. In Objective-C, we have to actually inherit from object, but in C++, we don't have to inherit from object, it's assumed. In Java, we don't have to inherit from object, it's assumed. If we want to inherit from another object outside of object, we inherit. It's not assumed. So we inherit from remote object instead of object, which means we're going to be using this in RMI. And we're not going to. Our hierarchy now changes, and we have a different build for how the object is going to function in a remote environment versus the local. So the object means that the single instance, as opposed to one of instances per request, only one single instance from Unicast, Uni1 cast object from a remote environment. So when they ask the register, remote object will be enabled. It will be called remotely instead of locally. Provides methods outlined in the interface that we just looked at a few minutes ago. Added an additional constructor that takes no arguments and sets the private the class variable to something. So we can have a default constructor because the object still exists. The object, we're still creating an instance of that object. So we can have a constructor. We just can't have one that we're going to call from a client. So it can start up and it can run. So now we're going to actually see this work. I'm going to go like this, 79. There we go, perfect. So I can flip back and forth. I still have my two windows opened up from before. I'm going to open up a third window right now because it will take 3 windows. New window. Change to. Oops, if I got that right. I did. Very good. I'm going to run everything from one directory, which is I highly recommend doing because all of the files that I have are in here in this one directory. So if I had them in different directories, I could load them from different, or if I had a class path set, I could load them from different places. But I'm making sure, in fact, if you want to be safe, just load everything from the same directory in different terminal prompt windows, as we're going to see. So the client wishes to use a remote object. It will need to know exactly where it is located. RMI registry coordinates or creates the phone book that records every object's name and address, publishes information about the objects or locations about the objects. We start the registry by typing in RMI registry. So it's the same RMI so you run RMI registry. It's a .exe in a Windows. It doesn't have an extension on a MacBook or on a Unix box. Running in the same directory as the other executables can be run by itself, and the background process will run in its own command line window. So you're going to type in RMI registry. We don't want that one. Let's get back to that window I was looking at. Window. It's just this one right here. So RMI registry. Doesn't do much. It just sits there. But don't close the window, because then you'll stop the registry. But I have the registry running right now, so I'm going to minimize the window, which is why I opened up a third window. I just needed to load it somehow. So open up a window, start the registry. Registry starts off with an empty directory. It has no directory. There's no way of actually invoking any objects. Nothing is loaded yet. I've just started the registry engine that says I'm going to be using RMI. So its only job is to provide locations to other programs, like a directory assistance, like that picture we saw with the registry sitting there. So we have to add stuff to it now. So now we need the Java program similar to the UDP that accepts requests from the remote objects. So the server program must also communicate with the RMI registry that it exists so that the clients can find it. And this is going to be ask the register server. And I will wait on the code, but well, actually, I'll just show you real quick. The code is going to be bound to a local host, ask the registrar, which is going to be the interface that we're going to create. So it knows about the remote objects, and it's going to load up. In fact, this is what it looks like actually. It's just going to load up. It's going to wait. It's the server object that's going to load the class module object that's going to run the ask the register program. So the server itself is a very small amount of code compared to the UDP server. Magic happens with a single line. The single line is the rebind, naming-rebind localhost ask the register. It binds itself. The server is just binding itself to the register and acting like a server. And it's empty. It doesn't have anything. So we have to load the object that we're going to load remotely as well. The rebind command is what actually performs the RMI registry. And this rebind command is used in the source code itself. Here we go. Naming rebind, which is right here. Naming rebind, which is part of the binding. So this is sort of like the abstraction of the datagram packet with the datagram socket that actually binds it. And this is actually based on the same concept as UDP. It's binding a port, but there's no open stream, so we don't have threads. So it's just like, it's very similar to UDP. So the first argument, the remote object's name and the directory where the RMI registry will be informed. So in our example, we're going to use a local host. I'm going to use localhost on this one as well. And, oops, what happened here? Only problem with loading it this way, my mouse is too sensitive. If the registry was on a port other than the default 1098, it could be specified at a place with a colon next to it. Otherwise, if you don't, you're going to put it on the default 1098. So it still uses the concept of the local host, and it still uses the concept of a port, and it's still using sockets, believe it or not. But the sockets abstraction is enclosed with the registry that we just loaded, the RMI registry. And it's still sending packets back and forth. But the packets are requests to invoke objects. And then it's the object invocation that's sent back. And then we have the RMI registry that manages everything instead of the TCP connection, instead of the TCP managing everything. So now, the second argument creates an actual remote object. So the server is going to make an instance of the object, accept requests from the clients. And most importantly, it's going to have it's going to create its own, instead of creating its own instance, it's going to create a single instance of the ask the register object that's going to sit there waiting. Here, went too fast. Mouse, oh, there we go. So here's what the client code looks like. And I'm going to load them both in a few minutes as soon as I get my PowerPoint back to the right one. So I think this is the right one actually. Hold on one second. We loaded that. No, we didn't load this. It went too far ahead. Hold on. This is where we left off. Okay, so moving forward, the RMI version has the single instance rather than the multiple instances that are created. So before we can run the server, we need to create what's called the stub. The stub is the placeholder that's going to hold the objects, if you think of it that way. So the stub class for the remote objects that will be used by the server. So we use an RMIC utility to do this. So the server does not exit. The RMI registry still has an open reference to it, continuously available for incoming requests. So now we have a server. We'll run it from a command line. So we run RMIC that creates the server stub for Ask the Register remote. And then this is the server that we're running, which is going to be Ask the Register server. So this is hopefully where I'm going to get this correct when I run it this time. So I'm going to take one of these other windows. I'll take my server window as I had before. And hopefully I will RMIC, spell this correctly, Ask the Registrar remote. And it doesn't do very much. Mine doesn't do very much. It doesn't come back and say anything. It should have said server was ready, but we'll see. Ask the registrar remote. Okay. We'll see what happens. It may or may not run. It was supposed to come back with a little status feedback, which it didn't come back with, which means it probably didn't register, but we'll see. So now we can see the results of the running clients if we run the, hold on a second, let me go back to the correct slide. That didn't load. Hold on one second, my mouse is, let me just make sure I'm running the right one. Ask the register class. Okay, that is correct. I know why. I didn't actually load the server. I loaded RMIC, but I didn't load Ask the Register server. So I did miss a step, actually. Hold on one second. So I've got the RMI registry open. I ran RMIC to set the Ask the Register service. Now I actually have to make an instance of the object, so which I haven't done yet, which is why I'm missing a step. So over here where I've run the RMIC, now I'm going to run the Ask the Register to create the object. So it's Ask the Register server, which is what I'm going to run. So the RMIC is setting the manager that's called Ask the Register remote. That's going to load the interface. It's actually equivalent to loading the interface to the RMI registry. Now I have to load the object. The server's not loaded. So I'm going to load the object. Ask the Register. If I spelt that correctly, and I've got it on the bottom of the screen here so I can compare it. Ask the Register server. Okay, Ask the Register server is ready. So just to review just one more time. Start the RMI registry in a separate window, which is what I did here, and I minimized the window. Keep that window running. Load RMIC in another window. Doesn't really matter because RMIC just comes back. You don't have to do it in the same window actually. RMIC sets the interface, that interface file that we had called Ask the Register remote. This is what we call the interface file. Registers the interface file with the RMI registry, makes it available. Last, load the server so that the object that the interface is pointing to that has those methods that we're going to invoke are available. We have to make an instance of it. We're making an instance of the server that we're loading on the same computer. It's all being done through the terminal windows, but theoretically we could have done it elsewhere. We good so far? I know it only has one step. We just load the client next and connect. So we're going to close this window because I have the server running in it, which happens to be in the same window I ran the RMIC in it. I registered the interface with the server. Now we have to create a client and access the remote object using these clients. And the client's got two things. The client needs a security policy, and the client needs to be changed so it doesn't load the local student doesn't load a local object, it loads the remote object through the registry. So first uses the same class, so naming the server did the contract for the RMI registry. So we have that already. So in this case, we're going to ask the registry for the location of the remote object, which is known as ask the register, because we just loaded ask the register objects. We have ask the register out there in the ask the register server that's been loaded already. So note that we're going to return the reference to the interface we initially created. So we have the interface for a naming.lookup remote server. So the client is essentially, why do I have an auto recovery going on? I don't know. The client is essentially going to ask the register using the ask the register interface. So we create a new instance of the interface that's out there, and we say, where's, this is the method that we're going to run. And the client code actually, when I get all done running the example, I'll show you the client code because that's the interesting part. Not interesting, but that's the part where you have to actually set the information. Now if I run the client, I can run, let me open up another screen here. This is the one I was doing my client in from the TCP, so I'll run it here. Let me make this, I want to get this so I can type without typos. So I'm just going to, so now I run Java local student client, which is the client for the RMI program that's running. Localhost and we're going to send it 760 CS because it's hard set for this class. So come back and say, hey, your space available or something like that. And now we see that it has worked. We see that the local client is running, called 2 arguments, remote server, localhost. It's sent, the class was CS483. The registration status is you are registered. And if I go back over to the client, to the registry screen, still up, the RMI server over here says it's received a remote invocation from my IP address, 172.165. Which is not localhost, it's actually my IP address, which it parsed out. Registration status requested for CS483. So the client asked the register the register looked at the interface, found the remote object, the server that was loaded, found the object that was loaded in the remote object, invocated the method, and sent the response back to the client. Sounds like a lot more steps than UDP and TCP, but it reminds me of UDP actually. It is UDP. Instead of and it's actually sort of a hybrid of the two. We don't have a stream. The client now can go away. I can have another client. I can run this again, and I can say, this time I can say 555. And this one's going to come back and say, there are no positions available to be registered, because this 555 is not the one it was looking for. It's looking for the other one. And then over here, I can see it came in from the same client. But now, let's say, for example, you're going to have a different IP address. But if this port on my computer were open, which it's not, you could connect through my IP address 172.165.134 through the local network and call that remote object and ask if CS999 was available. And my remote ask the register object would invoke that method and see that it's not available and send you that message back, and you would receive it on your client screen. So it's kind of a demonstration of how RMI works. In the real world, we'd load this on a server, we'd open up the ports, and we'd have internet applications connecting to the server and performing method invocations on those objects that were on the server. Why do we want to do that? Because then we can hide all the information, put it on the server, and not worry about security in terms of being able to like CGI or having, because it's ran through the RMI registry, the interface is controlling all the methods that are allowed to be invoked. So we can't invoke a method that interface doesn't contain, and we can't invoke objects that aren't part of the registry, that are like on somewhere else in the computer. So through this concept, we can create small programs, Java programs, objects, and have tons of objects that perform activities on the server. What can these activities do? Well, they can connect to databases and retrieve information. They can run reports. They can do statistics. They can serve up any functionality needed for applications. So you can create really thin clients that have Java enabled on them and run through and connect to the server. Because this client here, this client was just running a program. This client wasn't using RMI. It was just connecting the local, and I'm going to take a look at local student client in a few minutes. It's just connecting the local host. It could be running on a cell phone. It could be running on a, on a computer. It's just, it doesn't require very much. All the activity, all the objects, everything is being performed on the server through the RMI registry. RMI registry is on the server. It's not on the client. So, and these would be the pieces out here. So let's take a look real quick at the local service just to finish out. My JGrasp died again. My computer. I shouldn't complain. Shut down. Discard edits. I don't think I wanted any of those edits anyway. I don't believe I have the client code here. Or mid. Oh, actually, let me finish out one concept here before I forget, which is relevant. Let's go back to the server output. So the client example, we saw the server output live, so we don't really need to look at this screen here. Well, let's go back here for a second. Okay, so let me just finish this out real quick. So we saw the activity on the server. We saw that it was registered. Students requested this, came from this IP address. So we saw that live. So now we have this concept of a daemon. So what we just ran was one RMI server, and we ran one server object, and we had one client connecting to it. Previous example requires you to run a separate Java application in a server capacity to register in the remote object. So we're going to do this for every single program that we're going to write. That's kind of tedious. So if we wish, we can make multiple objects, multiple programs that are available through the remote objects instead of just one, which is what we just did a few minutes ago. And if we don't, we would need a super server that registers one of each one of the objects. Well, the super server, the expanded RMI registry is the RMI daemon, and you run rmid. So to solve the problem, use the RMI daemon as a background process. You have one process that will replace all of the other server processes that would be created if you were to run each one of these objects individually. So rather than loading up what we just did, had a separate server with a separate object and went through a separate interface, we combine all of the different objects that we want to do, and we run a daemon object in the background that manages everything for us. So it's just basically loading a different executable and making it available. So one process replaces all the separate processes. No adjustments to anything is needed. So we have this. So instead of having 1, 2, 3 pieces, we load the daemon. The daemon acts as the major router. So it's another level of control that we load. It runs in the background. So client still goes to the register. Register still comes back, returns the object information to the client. The client then invokes the method object through the daemon. The daemon figures out, what object are you talking about? Goes out and finds the object. So it instantiates the remote object. Not previously done. If it's not previously done, it instantiates the object. If it is, it services it up. Functionality gets sent back to the daemon sends it back to the object that requested it, to the client that requested it. This is an optional part. However, if you're running a full-scaled server, you're going to use a daemon because otherwise you're going to have it's too much. You have different processes set up for each one of these. You have different servers set up. Just use one server, load on the daemon. The daemon figures out which remote object you're talking about. And we have many different remote objects that we can put into this scenario. The code is the same, you're just running a daemon in the background instead. So the functionality is identical. But it replaces multiple running processes for this. So it takes and makes it more efficient. So the remote object we created here, the ASCII register last time, we modify, make it an activable, we modify the activatable object. We make it activated instead of activatable on demand, To clarify, we rename it the Ask the Register remote. In the example directory, I'm not going to run it, but you can run it. You have to load it up all over again. But this time you run a different version of it that's going to be the activation one. So it makes it activatable through the daemon instead of through the registry itself. So making it, instead of inheriting from unicast remote object, you're inheriting from activatable. So you changed one line of code actually in the server, and now instead of running from a one cast, one instance of that object through the registry, you're running it from, it's just activatable. So when the server requests it, you make an object of it. This also prevents you from having to make an instance of every single object before the server is actually ready. Because you might have tons of objects, and none of those objects might actually be needed until someone uses them, and if they're not needed, or they're very rarely used, why make an instance of them and have them hanging around out there? So the daemon allows more just-in-time activation of the objects as well. Saves memory. Only when it's called will it actually be activated and actually be used. So it does, again, conserves the resources a little bit more. So the application with the daemon service running in the background, it's the same application we just saw a few minutes ago, but there's one line that's inherited from activatable instead of unicast object. And you can go ahead and run through the example on your own with the daemon and see how that works. These references still work. If you're looking for more information on RMI, I believe that they are still available. I just checked them a couple weekends ago for the weekend class. So. Meanwhile, the last thing I wanted to do for you today was to show you about my JGRAS died, so I'm going to bring it back up again. Show you the source code for the client, actually, because that's the interesting part, which we didn't really see yet, and the slide didn't really show it. So you can more than welcome to download that, and I'll make the file, I'll make this, all the source code that's included in this example, I'll put underneath the video so you can see the link to it. I know it's probably underneath it many times, but at least you'll have a quick reference to it. But the Ask the Register student, this is a local student client. The policy, let me just show you the policy. There's two pieces the client actually needs. It needs a policy file. And the policy file, which I didn't actually mention in the lecture, opens it up to make it so that it can communicate. Otherwise, it's going to be blocked. So this allows the local client permission to use the network and make outbound connections to the server. And I changed it to localhost instead of alpha here for my computer. If you use localhost, it doesn't matter what your IP address is. And so it will give you permission for socket permission. If you don't do this, and this is just a text file that you save with the name of the class.policy, stick it in the same directory. If you don't do this, you're going to get a bunch of Java security errors. Permission denied, this denied, that denied. And it's probably one of the hardest things in terms of troubleshooting your program. The policy file is in the examples folder. So if you just take that folder and do what I did, unzip it to the desktop or unzip it somewhere, run everything from that folder, you have all the pieces the example should work flawlessly for you. There should be no configuration. When you start building your own RMI applications, then you'll have to remember, oh, I need a policy file for the client. And the policy file is only for the client, runs on the client computer. You ship it with the client program when you're going to run it. And this is kind of liberal. It's just opening up. You can actually add more stuff to the policy file. Ability to read files, write files. It protects the client, if you think about it. Because, you're going to open up and you're going to let traffic in. You're going to allow the client to exit out through a port like that. So Java provides a little bit more security. In terms of the local client, it's got a remote server string that's going to be taken, and then this is trivial. This is not that, this isn't, all it's doing here is saying attempt to locate the register remote object. Let me make this bigger. I keep forgetting you're not looking at this. Keep forgetting it's so small on your screen. The client looks the same as the regular client that wasn't using a remote method. But instead of making an instance of the object, it's doing this. It's attempting to locate. And we're using a try and a catch on it because it's a network application. If we don't have a connection, we can't, if the try fails, we want to be able to catch it. So here we're saying ask the register interface. It's making a request. Excuse me. It's making an object that is of the interface type. For the naming lookup for the remote plus ask the register. So this is the line here that's getting the object, this particular local object, to ask the register RMI interface. Where is it? When as soon as it makes the RMI interface is bound to the RMI registry, because we loaded that up using RMIC. We put the stub in there we put the stub of this interface into the registry, made it available, and we just asked the registry. And so this is the not too much code. And then we find out what method we want to run, and then we run the method. Here it is, the registry.setClass, which is what we called the registry. Imagine now you can probably see why you can't use a constructor object. How are you going to invoke a new instance of that object? You're just running a method. You're not even making a new instance of that object. The object is already created and it's residing on a server. So in essence, what we've got then is just a naming lookup through an interface, and the interface is going to be of the type, or the object is ask the register interface. So we load up new interfaces for all of our applications, and our clients ask, the register interface, or you can call it something else, the XYZ interface or something like that. Usually you're going to name the interface the same as the object, so you can remember what the interface is called. So, and you're going to name obviously you're going to name the policy file, maybe the same as the client, so you know which one that policy file goes towards. There's some flexibility in the naming, but as a general rule, it's nice to keep things organized by the name of the remote object essentially is used for everything, so you can keep track of what's supposed to be connected to it. What does this note say? Normally we should tell the object what class we want to ask for. Yeah. We can use a silent option, not actually tell it what class. This is the argument here. Just keep it silent. We don't know what class. But here's the remote invocation. This is the remote invocation right here. That's the remote invocation method, the RMI right there, which is one little line. Looks the same as if the object was controlled locally. So the only thing different is we go through the interface instead of going to the object directly. We can replace this stuff here with new instance of the object, made it locally, just like what you've been doing so far in Java. And the rest of this is just going to go through error checking, checking to see, printing stuff out to the screen as we saw before, and checking the exceptions of the problems that might handle. So, all right, well, I hope you enjoyed the RMI example and the UDP. We put the pieces together finally. And we can kind of see where this is an extension off of UDP, maybe. You can see that? And it's kind of not really the TCP, because the TCP is more of a stream-oriented and a thread-oriented. But we have that thread of the RMI registry running. In fact, it's still running. We still have a background process going on here. So I can leave the RMI registry running on this computer, or on this server, if I were a server. And I could load other stuff into the registry as well. So it's just a matter of design. If I were going to run a lot, I'd run the daemon and load it all up into one daemon registry. The daemon is just an add-on piece that puts all the pieces together instead of creating separate processes for each one of them. So next time we have IP on the menu. So now you can do the project for RMI. You can use this source code as an example. And the only way, you can't learn it by watching me play with it. You have to actually work with it yourself. So that's how you're going to learn it. So questions, comments, or concerns? No? I had enough for today? All right, time for lunch? Okay, time for lunch. Let's go to lunch.